Well, this is the presentation of systems engineering journey, which main character is the S80 Submarine. So the journey has been, will be presented in three main stages: the acquisition program, which is document-based, the delivery of the S81, means that from building to through life support transition, and the through life support as we expect it to be. For the legacy, we have in the acquisition program a typical V process systems engineering, in which we start with the requirements, then we develop the engineering and design using several tools. We have a product data management system, which develops, among other things, a virtual model. And then we transforming the engineering bond into an M bond, we can develop purchasing and the construction. So the process is the requirements management, then we move to the product design, everything based on documents. Then we move for the design verification, everything based on documents, then product realization based on documents, and the verification of the product, which is also based on documents. The whole system, even having digital support, is based on documents. PDFs most of the time, but documents at the end of the day. Then we get our S80 as designed, as built, and as delivered. And as soon as we deliver the S81, there is a breakthrough in the systems engineering process, because Navantia is a provider of services for many navies in the world, but the current maintenance of the units is based on a detailed scope, which is prepared by the Navy, and then the Navy places a contract to Navantia to perform the scheduled maintenance. And this scheduled maintenance is a deliverable of the respective acquisition program from the builder to the navies. In the case of the S80 is Navantia, who is providing the scheduled maintenance. So we are all over the world providing services to many navies. And another point in this breakthrough is the new vision of the Spanish Navy Sustainment Admiralty, which in his document related to how the Navy harbors have to be by 2030, they talk about availability of the units, efficiency, so do it cheaper. The facilities have to be environmental friendly, not so important in the ships. And this is based on the knowing the current status of the fleet and prescription of what maintenance has to be performed. The system described in this vision is more or less like this. Every facility or every asset of the Navy must be linked to a data management system and connected to some time of prescription. These systems in boxes, systems engineers, we used to love boxes, is an integrated sustainment system on the top, and then some comms which are needed, data management, and the model of the different assets that will allow the prescription of the maintenance of the units. In addition, the sustainment program of the S80 has this the following roadmap. So we have finished the transition phase where the Navy and Navantia have been preparing how the through-life support will be. Then we are now running the first through-life support phase, which is we are learning from our ship how to monitor the availability and the performance. And the second phase has two very interesting bullets, which is transferring risk to the industry. This means that the Navy wants a different type of contract with Navantia, other than a list of tasks with a fixed price, and the payment linked to availability and program performance. This means that we need to build a team together with the Navy, Navantia, who is the technical authority, and will be managing the configuration of the boats, and ISDEFE, who is a Spanish state-owned company who is devoted to through-light support services. And then this team, this is the logo and the motto of the team, which is efficiency, safety, and availability. So this is in the motto. We have the three main targets of this program. So the objective of this proposed solution is provide an efficient sustainment based on safety and availability of the fleet by assessing the unit's status and predicting the performance in terms of the executed maintenance. What a statement. Then the summarizing the situation is that we are in the life cycle support stage. We are providing at this moment support based on a set of documents related to as delivered configuration. A new through-light support model is in the Spanish Navy's mind, which must be based in availability and performance as KPI. The risk transfer to the industry, efficiency as an objective, and the safety assessment as maintained of the boat. So at the end of the day, we will need a predictive model to manage all those KPIs and all those requirements from the Navy. Then let's get started with the through-light support systems engineering, which is the new path. Then for availability prediction, performance and safety assessment prediction, current asset status as input, and cost of maintenance linked to asset availability. We are not alone in this task because we have as a reference the US Navy product support, which is a very ambitious program that is not only supporting the units but providing training and logistic support in any manner to the US Navy. The situation, if we analyze it, we have a threat in Navantia, which is a high-risk contract, but we have some strengths, which are a deep knowledge of the product. We have expertise on ship repair and services, and we have a very powerful PLM solution implemented who supports advanced engineering. The opportunities we have is having the portfolio a new business model, which is provide advanced services to other navies, a close collaboration with customer that will enable us to know the operational details of our ships. And as weaknesses, we identify our engineering team is document-based and our legacy information is not model-based. How to fight those threats and weaknesses? Trying to agree in the contract part, the ability assessment, and reduce the risk by engineering the solution in the contract price. Then for the engineering team, which has to transform to a model-based team, is we will train the team, and we will try to change the culture from subsystem document-based to capability model based. And the acquisition engineering and simulation were not model based, but we have to transform it in model based to assess the capabilities of the boats. Then we made a proof of concept, which is the diving control system, which is a system of systems inside the S80, which has not a particular node in the product structure because it's composed using components from different subsystems and has a little bit of electronics, a little bit of software, a little bit of mechanical systems. So we have almost, it's a very representative subsystem in the ship. This is our proof of concept. Then on the other side, we have our engineering solution or tools. Our engineering tools are supporting what we call the systems engineering diamond, in which we have on the lower part the classic V system design and construction, and on top we have modeling and simulation that will allow us to build a digital twin and improve our design and verification process. So the process that we follow for this proof of concept is as shown here. We have 3 lanes, which is a runs engineer who is assessing the reliability, the safety, and the availability, and the systems engineer who is modeling and managing the configuration, and a simulation engineer who is building simulation models as required to support the verification process. Then in this area we are using Capella with the integration with Siemens Accelerator, which is a system modeling workbench. In this part we are using Team Center for managing the configuration and the verification. And in this part we are using Amazon for this proof of concept, but we can link in the future to more detailed simulation. Amazon is a 1D simulation tool from the Siemens portfolio. Then using system modeling workbench is naturally focusing you to the Arcadia methodology. So this is the one we follow in the process. And we started by defining our operational architecture diagram, in which we have set the capabilities that are required from our subsystem in this analysis. Then we move to the system analysis, and we still having the operational capabilities for each of the capabilities is developed in a single diagram with including functions and actors and so on. Then we move to the logical analysis, and then we allocate all these functions and interchanges to the subsystems that we have already defined in our system, in our bigger system. When we move from the logical to the physical system, we have made a step back because the domain specialists are incorporated to the project, and then they refine the analysis by making a functional analysis again and developing the complete analysis, the logical architecture and the physical architecture, starting from refining the functions. This is the input to this process, which is a logical system with very small functions. And once we finish this process, we have, for instance, in this case, we have double the functions in terms of having more availability or more backup system for the main functions. Then we develop our physical architecture for the whole system, including internal and external actors of our system of interest, and for different, we identify all the connections and all the interchanges between different systems, and we build libraries to represent the every subsystem in this system of interest. Using this library approach allows us to reuse the design of the S80 Submarine as it is. This is all the artifacts that we've been using through the system analyze to the physical architecture, which are the usual artifacts from Capella. And then once we finished our model, we go to configuration management. In configuration management, we have the export of our model to Teamcenter, which is the tool we are using to identify the changes and to manage the configuration. And then we have a capability approach to our model, in which we have used all the libraries we have created in the previous stage, and we are developing capabilities. We can track, for instance, a functional change, which is devoted to manage depth and the trim. And then we have all the involved functions, and in this capability, and we have all the functional interchanges. And then we can manage the configuration, release all those items, and to know exactly which configuration is in force in every moment. We have also in our breakdown, we are going from the subsystem to a module, then a component, and then the function, the behavioral component, which will manage the configuration of our simulation. This is the item that we will link to our configuration, to our simulation model, and the function at the very bottom of our structure of the model. Then we move to AIMSYN to build simulation model. And we build a simulation model in which we have models for the supply of power, or we have a model for the dynamic behavior of the submarine, and we have some output parameters that are that are calculated by the simulation model. Then our simulation model has also a failure simulation model, which is that we are using by identifying which parameters are relevant for the reliability and the safety. So we have as input parameters, we have the MTBF or any other reliability metric, or the operating time, for instance. We have an output parameter, which is the reliability. Then we have some failure triggers just to check what the system does when a failure is taken in place, and some output functions that are delivering the current output of the system when there is a failure, or in terms of any of the other input parameters. And all of this allow us to predict the reliability of a subsystem or a system or a complete system, and the failure criticity. So let's move to the verification of our capabilities. We are verifying capabilities in terms of assess the availability of the ship. Then we link our simulation models to the verification request. We link our capability. We are verifying capabilities, not requirements. And then we have some output parameters and some input parameters. In this case, operating time that we are simulating is an input parameter. The system reliability prediction is an output parameter. The reliability of any of the system parts is also a parameter. And we have, for instance, additional KPIs, which is the days to service prediction for a part based on reliability probabilistic distribution. And what is very nice with the integration with MSIN and Teamcenter is that we can launch our verification requests from the PLM. So what we are doing now is preparing a simulation, checking that the parameters, the input, in this case, we have some output parameters because there has been a previous run. But we are checking in this screen the parameters that are okay. Then we can, from this interface, we can launch we can launch the simulation. And then what is doing the system now is opening the simulation in the background, introducing the parameters in our simulation model, running the simulation. And when it's done, we have a message. Then we can close, click on upload, and then we have our output parameters back in our PLM, in our verification request. So we can verify if we have some threshold, we have passed or failed. And we have our verification run without opening the simulation model. So where we are now with this project, we are a part of a much bigger system, and we are just focused on the S80, which is a number of assets. We have completely developed this proof of concept, which is the diving control system, and we are now developing the whole ship model to assess the reliability of and the availability of the ship of the complete ship. So at the end of the day, what we want is a back-end solution which is based on systems engineering, configuration management, simulation, so on. And in
5 minutes left.
in the front end, we will have the PLM, the virtual mockup, some performance metrics, cost metrics, and reliability metrics, which is the promise. We are not here because we don't have the model of the whole ship. The promise is to provide to the program, the through life support program, for decision making information like this, which is the predicted cost budget ratio in the y-axis, in the x-axis the predicted availability, and then the size of the ball is the number of the shutdown days. So you can have a very high performance with high availability, high cost, but with a higher number of shutdown days, or a small budget solution, which is not so good in performance, but has a very short shutdown days for the maintenance period the a lower availability. And what are the key takeaways? Or the three main things to take into account. First of all, that sustainment of naval vessels has evolved from a preventive to availability-driven model. Second one, that the S80 must evolve from a document-based to a model-based systems engineering just to support this new sustainment model. And that MBSE provides new high added value capabilities to our portfolio in order to be competitive and be state of the art for sustainment of naval ships. And that's all from my side. And I'm ready for your questions.
Okay, thank you very much, José. The first question is from John Rowe Erasmus. Hello, John Rowe, by the way. So the question is, you showed that you organized the node physical components in libraries. There is a screenshot with that. However, I see in the diagrams that you also use behavioral physical components, which are usually allocated to node components. How do you organize the behavior physical components in the Capella project?
Well, we've been facing some issues with managing the behavioral components, and at the end of the day, we have not been able to reuse all the behavioral components. So what we are using is a reference, an additional reference, which is some kind of property in the model to remember the configuration management guys that they have to join together the simulation model of the same behavioral components. Because I don't know if this answered the question, but we have had issues with Capella and the integration with Team Center to manage this, and we are using, let's say, a degraded solution for this, which is using some properties to link different behavioral components to the same simulation model, for instance, or things like this. I don't know if this is the question, the reusability. We have had issues with that.
Okay, but do you nevertheless put your behavioral physical components, I mean the blue ones, are they also in libraries like the node components?
No, we have libraries at the subsystem level, and that's why we have several problems with using.
Okay, well,
we have the behavioral components library for us is the simulation space more than the.
Okay.
We build there and then we link to different behavioral components when the behavior is the same.
Okay, well, I think that's all for this question. So let's move to the second one, which is basically just understanding what you said about the Siemens offer that you're using. Is I believe it's a Siemens accelerator, but not everybody seems to be familiar.
It's spelled accelerator. It's an X on front of it, and it's the integration of softwares of any kind. So you have electrical solution, you have mechanical solution, you have model-based, you have requirements, you have all the suite of Siemens who is providing services to the digital industry is called Siemens Accelerator. I don't know if I can write it in.
So did you build a business case for utilizing MBSE to deliver this work, or was MBSE considered the only viable approach for this work? And if you were required to build a business case, what KPIs or ROI metrics would you use?
We had the model-based, the system that we've analyzed was almost developed almost completely in a document-based manner. So the model-based approach with the other set of I mean the PLM, the simulation, and so with all these ecosystem of tools allows us to run verification from the PLM, which is for us a capability that we couldn't find in any other of the options that we had to face this project. In fact, this is a proof of concept, so we didn't know if we will succeed, but we did, and now we are scaling. So we developed several proofs of concept, and that one of them based only in simulation, but was quite hard to manage the configuration. If you only have simulation, is something missing there. And the ship is not in our hands. We are not operating the ship, so we have to update the configuration with things that happen that we cannot manage. We cannot predict the changes that have been made in the ship. We need a tool that can update and easily assess which is the new performance of the ship. So for us, being able to assess from just to update the configuration by introducing parameters in the PLM and assess the capability in minutes. This is where we are now. We can update the current status of the unit and in minutes assess our capability. The only ecosystem of tools that allows us to do that was the one we fused from all the things we have assessed.
Okay, great. Thank you for the answer. And by the way, did I understand correctly that you consider this proof of concept to be a success and you are starting to model the rest of the ship components using the same approach?
Yeah, we are scaling now this project to the whole ship. This was a proof of concept in this stage of the TLS program, which is prepared for the different model of sustainment. There are a lot of projects in ongoing. One of them was that one, but for instance, we have also machine learning applied to component reliability, or we have some others like devices on board to provide a more accurate configuration management. So we have a set of initiatives ongoing. This one is one of them.
Okay, perfect. Well, next question then. There is a beginner question that raises some interest. So is it possible to do trade-off analyses in Capella? For example, if I change a value of a parameter in a requirement, is it possible to see which other requirements are affected, other subsystems or components that get affected, and so on?
Yeah, of course you can trade off analysis in Capella, but at the end of the day, Capella itself is for modeling the architecture. So you need something else to make that trade-off. It's not a design; it's an engineering tool. So the trade-off needs to incorporate some additional tools. But of course, you can manage two different configurations by modifying a parameter in a requirement or whatever. Yeah.
Okay, thank you very much. Another question is raising interest. Can you share some details on how your Capella model is tied to simulation? Are you using PVMT, for example? And can you give a bit more insight?
Yeah, well, at the beginning of this project, we didn't have all the reliability parameters, the pass-fail requirements. So we didn't push the parameters from Capella. But in the next stage, we will write the parameters in Capella and then populate them into the PLM, so we can push the parameters from the model. In this project, the parameters are managed in the PLM. because we didn't have when we started modeling, and then when we retrieve the reliability threshold, or the safety, it's quite hard because never have it done for a capability. We have requirements for the subsystems, but if you compound the different reliabilities, it's quite hard. So we had to ask for new thresholds for our capabilities, and as far as we didn't have it from the very beginning of the project, we decided to keep it in the PLM, but we will use PVMT to scale this project.
I see you mentioned availability and days out of service. Over what period is this counted, and do you define the availability?
Well, there is a Navy staff requirement always regarding the maintenance periods. So at this moment we have fixed periods of maintenance through the whole life cycle. It's scheduled. I mean, I think there are more or less 11 months. We have scheduled one, put the boat out of the water more or less once a year, or 1 year and a half. We have some periods in between that perhaps are 2 weeks, and we have some periods that are longer, which is the overhauls. A submarine is absolutely disassembled and reassembled every 7 years. So it's a requirement for us, the period. And in terms of the requirement, the availability is the metric used to be days at sea per year in the period between overhauls. So if the period between overhauls is 7 years, for instance, you have the metric used to be, for instance, 270 days at sea, which is the submarine has no maintenance task for 80 days or 85 days a year, only for 85 days a year, and the rest of days must be available. This is one of the metrics. This is the standard we have now, but not the one.
Thank you very much once again.
Okay, thank you, and very meaningful questions.